Alrighty, so we're gonna start with child on merry-go-round, since that's the first one asked for. So we've got a child sitting on a merry-go-round that moves with this speed. I'm assuming that's the speed of the child. Let me see if I can't make this bigger. That's a little bit better. And they want to know the centripetal acceleration and the net horizontal force on the child. So your Y for this one should have been a force diagram. And I probably would have drawn it from a side view, or I'm going to draw it from a side view, kind of like the one that we had yesterday, where we had the merry-go-round kind of looking like this, with an axis through the center, and here's our child sitting on it, little box. And we'll assume that the merry-go-round is rotating in that direction. So, let's see, the child would have weight down, would have a normal force upwards, and would have a frictional force inwards like that, and be accelerating towards the center since they're moving in a circle. And that might be the wording that you want to include there underneath this. Might be, you know, something along the lines of must be accelerating towards center since moving in a circle. You know, something along those lines. So it asks us what is the centripetal what's the acceleration and what's the net horizontal force on this. Really, we're just using the definitions from our equation sheet. So if we start with part A, equation sheet tells us the centripetal acceleration magnitude is the speed squared over the radius. It gives us the speed, it gives us the radius. Yay! All done. Then for part B, radius is defined how far you are from the center. So mine says I'm 1.2 meters from the center. So that would be radius. Yep. And then I can do the sum of the forces in the x direction equals max, our Newton's second law there from our equation sheet. Only have one force. Our frictional force, I'm going to call it towards the center, is positive, bless you, equals MAC. Oh, wait a minute, I solved for AC last step, and it told me the mass. So I can find that frictional force, which is my net horizontal force. So I'm just solving for my frictional force there. And that'll do it on that one. You know everything. All right, so 979 was the next one asked for. And this one, we've got this rotating drum of a clothes dryer with a radius of this. And we're given the acceleration at the rim of the drum. What is the tangential speed of the rim? This one really centers back on the, if you, kind of like the last one, is that you need to realize that the acceleration at the rim would be centripetal, i.e. causing the direction only to change. So you have this centripetal acceleration at the rim because the acceleration that we're going to assume that it's moving at a constant rate, and we're just dealing with the circular motion. So you fall back on reading your equation sheet, v squared over r. They give you a, they give you r. Hopefully you can solve for v. Yay! All done. All right, so 8.56 was the last one asked for, so we'll go ahead and do that one. This one, nicely, they've already included the force diagram in the problem for you. So really all you needed to do there was reproduce their diagram for you. So let's just do that right away. That way we can get that out of the way. So 8.56, we have the Planck, we have F1, F2, and then I'm going to call it the force of gravity, which is, of course, the weight. They used the notation mg, same thing. Remember, it's completely up to you. They're asking you how much does the child weigh? Well, that's a good force diagram. Now I just use some of the forces in the y equals 0 since there's no acceleration. That would mean, and I'm going to call up positive, so F1 plus F2 minus F sub g equals 0. So F1 plus F2 equals F sub g. And I'm given F1 and F2. Yay! All right, so 9.81. We got this car going out, going around a corner of this with this speed. Gives us the coefficient of friction. Assume the car doesn't hit what force is exerted on it by static friction. Yeah. So, be good to do. This is the situation that we ended class the other day with. You know, we had that little video. So I'm going to draw, let's see, there's the car. We'll even give it little tires. It's heading at us. We'll say the point that it's going around is there, and there's the ground. So the car is actually coming out of the page at us. So we'll draw its velocity vector like that. So let's see. It would have weight down and normal force up, and then a frictional force towards the center, and it would be accelerating towards the center since it's going around in a circle, or going around a corner at least. So it's in circular motion. And they want me to find, let's see what, they want to know the frictional force, right? So the frictional force is in the x direction, so it seems like that would be a good place to start. So sum of the forces in the x equals m acceleration in the x direction. I'm going to call towards the center for this motion positive. So that would give me frictional force equals MAC. Oh, and I look at my equation sheet and know that AC is V squared over R. And let's see, they give me M, they give me V, They give me R. All done. Yay. I got that from my diagram. See, Aiden? That's why it's good to do the diagrams. All right, so 5.102. One about Leonardo da Vinci doing his experiments with friction and wooden block, and what angle did Leonardo's block begin to slide? So, I know it's shocking, but we're going to do a force diagram again. So, let's see. I feel like my incline should point that direction. So my incline is going to make an angle of theta. I'm going to have this block on it, and I'm right at that point where if I tilt it up any higher, the block's going to begin to slide. Remember, frictional force, which is what is holding this in place, is one of those forces that's only ever as large as it needs to be. So the whole time, if I had started this at 0 degrees, the whole time up to this angle, the frictional force is actually increasing as more and more of the weight is directed down the plane. So I'm at a maximum now. So I've got the weight of the block acting down, the normal force, which is perpendicular to the plane, and I have a frictional force, which is parallel to the plane. So my only force that's not parallel or perpendicular, and I have 0 acceleration, of course, is this one. So I need to do the components here as we were doing the other day. So this side would be Fg sine theta, and this side would be Fg cosine theta. And that would be my proper force diagram for this. So now, let's see. Let's start with let's do the parallel, the perpendicular forces first. So we're going perpendicular to the plane. Sum of the forces perpendicular equals 0, because since there's no acceleration perpendicular to the plane, I'm going to call away from the plane towards the words force diagram as positive, and I'm going to call down the plane positive, and I guess I'll call up, it doesn't matter, down the plane positive. So I have two forces. I've got the force normal, which points upwards, minus Fg cosine theta, that equals 0. So those are my two perpendicular forces to the plane. And I can do a little algebra and say that the normal force is mg cosine theta, right? Then I kind of at a standstill. I don't know what m or g or theta. Oh, I know g because Leonardo lived on the Earth, so we're going to use 9.81 newtons per kilogram. But I don't know theta, so I'm kind of stuck there. So let's do the parallel side of this, see if we can get any further. On the parallel side, sum of the forces parallel equals 0, no acceleration in that dimension either. And I said I was going to call down the plane positive, so I have Fg sine theta minus the frictional force equals 0. So the frictional force equals mg sine theta, right? Just a little bit of algebra and remembering that the weight is mg. And I can go one more step further here and remember that from my equation sheet, the frictional force is mu force normal, which is good because that allows me to bring those two parts together. So I can go and now say, oh, if I mathematically bring those two parts together, I get mu mg cosine theta equals mg sine theta. Mu is the coefficient of friction. It describes how bumpy the two surfaces are to each other. Because I was looking for a way to join the two dissimilar equations that I had, frictional force and normal force, and I remembered, or I looked at my equation and remembered that, oh, frictional force is the coefficient of friction times the normal force. The friction is created when you have two bumpy surfaces that are held together. And now I can do a little algebra and find out what theta is. Now maybe kind of a trick. So, but you can solve it from there. No, I just used algebra. I didn't use any geometry. Yep, I'm given the mu. And I would look for things that cancel out. I'm afraid of mathematically going any further and people who aren't understanding it just plugging in a number into one thing. I mean, look at it mathematically. There's a lot of simplification you can do. A lot of mathematical simplification.